Hi everyone, my name is Sam Connerly, and today we're going to be going over our Physics 2 Lab 5. First, a little introduction to the lab. Our lab is to help us learn about Faraday's law. We're going to do this by observing a magnet fall through a tube of aluminum foil. We're then going to model this interaction using GlowScript, and we're going to compare the model with our observed data to check for accuracies or inaccuracies with what we calculated. Here are some quick results. The average time for the magnet to fall through the tube is 0.63 seconds. Using a computational model with mu, we see that the average time is 0.396 seconds. And using a computational model with mu 2.61, we see that it's accurate to our observed value of 0.63 seconds. So some important physics principles to remember is Faraday's law, which is the negative change in flux is equal to the dot product between the electric field over the length of an object. We also want to look at magnetic force, which is the force due to a magnetic field. This is equal to the cross product of the current times the length of a wire and the magnetic field. You can see these in action on to the right to get a better understanding. There are some other important principles we need to keep in mind as well, some being the magnetic field of a bar magnet, generic magnetic flux and the changes over time, Ohm's law, Lenz's law, the momentum principles, and just Newton's laws of motion as well. So some initial conditions. Our system is going to be a bar magnet that we're going to observe surrounded by aluminum foil. It'll also be experiences forces from the Earth, mainly gravity. And our assumptions here are going to be that only the forces on the magnet are gravity and magnetic force, the magnetic force of the aluminum tube. So the procedure for this lab is pretty straightforward. First, we're going to create a tube of aluminum foil, and we're going to measure its dimensions. We're going to determine the mass and magnetic dipole of the magnet, and then we're going to record a few instances of the magnet dropping through the tube. We're going to record the time it takes to reach the bottom and get an average for our results. And then we're going to create a model to compare the results of the lab to what we would normally expect and what we calculated and observed. So here are our observational results. As you can see on the left side, we have the length of the tube, the radius, width, total radius, magnetic dipole moment, and mass of the magnet. These are all of our dimensions and parameters for the experiment. And we can see the results over here on the right in this table. And if we take the average of those times, we see the average time to fall through the tube is 0.63 seconds. Then we're going to recreate this using code. The setup's going to be similar. We're going to input all of our dimensions and parameters into the code, length, width, radius, mass, dipole moment. And then we're going to plug in a simulation that looks at the behavior of the magnet as it falls through and experiences those magnetic forces and flux as it goes through the aluminum tube. And the results we see that with a mu of 1.824, which we've calculated in Lab 3, we see that the time isn't accurate to what we've observed. But when we change the computational model to include mu equals 2.61, we see that this falls in lines with our observed results. So to talk about that a little bit, using the magnetic dipole to determine for Lab 3, as we just mentioned, magnet took only about 0.4 seconds to fall through the tube. This is a lot less than what we recorded from the experiments and from what we've observed and calculated. But by using the magnetic dipole that simulates accurate results is by using a dipole moment of 2.61. And some possible sources for error here is friction between the magnet and the tube, human error, and just timing errors, maybe using our tools and materials. A little bit of further discussion. What if the resistivity of the conductor reduced as close as possible to zero? How the dynamics of the falling magnet change? Zero resistance would have a higher induced current, which would lead to more magnetic force, causing the magnet to fall more slowly. If there are holes or slots cut into the tube, this would disrupt the circular flow of the current, which would be less current, which would be less magnetic force. Therefore, the magnet would fall faster. And there also might be some issues with air resistance and airflow throughout the tube that could cause some changes. But that's it for me. Thank you, everyone, for listening, and I hope you enjoyed.